So I will be talking on 10-ish years, but it's 10-ish because I'm not quite sure. I've got a question of when did FreeBSD ARM64 actually start? It's some of these numbers, obviously, they're different times, points in time, and I'm not entirely sure exactly how you define the start of porting FreeBSD to ARM64. So I'm going to sort of go through some of these and give a wee bit of a history on them. So I'm going to start with the journey of, think back to about 2012. ARM has just announced the new architecture. And we're trying to explore how does this architecture actually work. So how do you understand the architecture? Or you can read about it. Documentation is always nice, but there may not be. You may have issues, and hopefully there's some source code that you could also read if other projects, similar projects, have been released. And you can always write something. Of course, you need a tool chain, and you need something to actually run the code you write on. So we're going to do some reading about it. If you're ever looking at the ARM architecture, you'll find I don't know how many tens of thousands of page document it is now called the ARM Architecture Reference Manual. It's the ARM if you see that. The issue is, I mentioned they announced this in 2012, and the first release of this is 2013. So reading documentation is good if there is documentation to read. The other source of documentation of things I can read is there were patches at the time released for Linux, but you may have noticed there's a thing called the GPL, and we've got the BSD license, and they're not exactly compatible. So we've got to be a wee bit careful doing that. You don't want to accidentally copy some GPL code into a BSD program and have it suddenly have to figure out what the license on that is. It'd be much easier to just do everything clean. So it was possible early on. It was a bit difficult to read things, but it was a wee bit difficult. Luckily, they had, ARM did release GCC and binutils patches. So I had a tool chain at least I could try writing something and see what happens. This turned out to be the main way I was doing a lot of my early work. And in late 2012, they did release what they call the foundation model, which was a very fixed platform with fixed hardware. It comes from a product this is a specific version of what's called the fixed virtual platform, which is a slightly more complicated tool, which comes from the fast models, which is a very complicated tool, which various companies use to test hardware before they have hardware. So I could use that to at least try running something, see what happens. And luckily, there's a Linux boot wrapper, which was BSD licensed. It still exists. It's still used in various things. So I can modify that, and I didn't need to boot into a BSD-like thing. Into Linux, I could boot into a BSD-like thing. And it was used just to get the model into a known state where I can do whatever I need to do. So I sort of, early on, get these two tools, get these tools together, figure out, and then use this to figure out how do you create, how do you actually create something? So I created this project, the ARM64 FreeBSD sandbox. And this is one of the possibilities of what we consider the start date. It still exists. I haven't touched it in over 10 years. So if someone really wants to see what the old code looks like, it's still there. So So the first piece of code that runs in the kernel is in a file called locale.s. And this was the first attempt at writing this. And there is some of this code still exists in FreeBSD. It still exists in FreeBSD. I have renamed some of the things, and some of the bits have been changed. And it looks like OpenBSD has some as well. Where I think they took some of the FreeBSD code early on and reused it, and they've gone in their direction as well and changed things. So that may be the first date, the start of FreeBSD ARM64. But this is now getting the boot wrapper runs in what's called exception level 3, which is the highest privilege level on ARM on ARMv8, and it's not normally somewhere where the kernel runs. So it just gets you into one of the lower exception levels, called normally EL2, which is more like imagine it's the hypervisor level. That's where you typically run the hypervisor. That's where the kernel would have entered at the time. And then we then have to drop down to EL1 to run the actual kernel. And so EL1 is the kernel level, EL0 is user space. So what we do is we need to do a little bit more configuration. And so this is me trying to figure out what this configuration is, write the assembly that would do this, and get into EL1, where we can then do things like build page table so we can turn on the MMU. Yeah, there's still got the problem of no documentation of how any of this should work. I think I had might have been some instruction lists, so at least tell you what they do, but nothing on how the page tables are laid out. So that's where looking at Linux was about the only thing I could do for that. So the way FreeBSD boots is we assume the MMU is off, or MMU is either on, but with an ID map, so every virtual address is the same as the physical address, or is off. In the early case, we just assumed off because that's what the boot wrapper does. There were no documentation, as I said, so look at Linux. But luckily, ARM added a nice instruction called address translate. So what you do is you give it a virtual address, you run it through this instruction, and you read a special register, which gives you the result. And that will tell you probably messed something up. And hopefully, it'll give you some information about why you messed up. So it says, are you, this level of page table walk is unmapped. There's nothing, it's an invalid mapping or something like that. And you then go through, you figure out why, essentially. When turning on when turning on the MMU as well, you've got the problem in that the MMU's on, and that includes for your code. So what I often had to do was I was running on EL1, which is the kernel level, taking the exception to the hypervisor level, and then try to figure out what just went wrong. That sort of worked. I got most of the way through page table creation. I did time passes. I moved to the UK. This has all started originally when I was a developer in New Zealand. I was going to give a talk in Malta, EuroBSDCon 13, and it was about something. It was about ARM. Obviously, I do ARM things. I was going to, and I saw Andrew Wuffer was there. He's going from ARM. I was going to ask him about documentation, and then they released it 3 weeks before the conference. So luckily, I didn't actually have to ask him in the end. I got that. So we can go, yay, I've got documentation. And there's an access flag. If you don't set this flag, all access is trapped to the kernel. That was my problem. And if you don't set this in the kernel, all access is trapped to the kernel. And then you have an access which traps to the kernel. As you can imagine, this is why you can have some issues with this one. So set this flag, and everything works. So possibility two. I've done this, we've got the MMU working, at least. I've got some C, always had some C code running there. MMU may be off. We load at a known virtual, physical address, so we can just build it as a static binary. Turns out there's more than just the startup code assembly in the FreeBSD kernel. And so we can move to a Subversion project branch, because this was well before our migration to Git. So yeah, FreeBSD is more than just locale.s. That's shocking, I know. So February 2014, I created a project's arm64 branch that was starting to think, well, okay, we've got something we can get into C. Why don't we try actually doing all the other bits that need to get into, we need to get FreeBSD running. We started with, we need a tool chain. Luckily, up until this point, I'd been using GCC and binutils. Luckily, Clang had added support in 3.3. Unluckily, we still needed to use binutils. We didn't quite have a linker, I don't think, until much later. And also unluckily, this was quite buggy. This was the first release with LLVM. And luckily, they did improve in later versions. And so we've got, I was looking at some of the old changes, and it's like, some of the later ones were remove a workaround for LLVM 3.3. Something was broken. By this stage, there was at least a bootloader, slightly better boot strategy than just run this random command, this set of commands to get you into the state you want. It was now actually some boot firmware, so ETK2, we could use EFI booting. U-boot hadn't been ported, I don't even think, to ARM64 at the stage, and definitely didn't have EFI support. The problem is the way that we built loader.efi is build an ELF file. This is on AMD64. Build an ELF file with, tell it, occasionally we have to tell it they use a slightly different calling convention because they use the Microsoft calling convention. We don't have that problem, luckily, on ARM64. And then use objcopy to create an EFI file. We still don't, as far as I can tell, have objcopy to build an EFI file. We do this. If you don't recognize, this is some assembly that says, build me a PE-cof header manually. We do have some macros, at least, to say this is a ARM64 machine. And you can do some basic arithmetic to give it offsets of things. What we have to do is build an ELF file and objcopy it to a binary. And this header magically appears at the start of the binary due to a linker script. And so when you do that, you actually get a proper EFI file. It's a bit of a pain to do but once you've done it once, it's fine. I will point out this was inspired by Linux. They do something similar with they can boot the kernel as an EFI file. So I did a port of loader. There were some cleanups there. It's a lot nicer nowadays than it was at the time. But still, the kernel's still more than local.s. I still have problems with all these things other than it's not startup code. What do you need to just build the simplest possible kernel? There's lots of functions that are machine dependent that you just have to have on every architecture. They may look slightly different on different architectures, things like copying from user space to the kernel. You're probably going to want to write that in assembly because if you fault in the middle of that, you want to unwind everything. Or you have to check ahead of time that you're not going to fault. So how about we just implement everything as panic, and we'll deal with it later. That was the strategy I tended to use. And the other problem is you may not know where, when you're trying to actually get into C code, or you may not be able to know where you are in the boot process. So having something like this assembly to do a put char, say, I'm here, come and get me, come and fix me, that was also useful. So I do this and build a kernel, try it, run it, find it doesn't work, figure out why it doesn't work. This is just a big iterative process. But after a while, you get to the first C instruction. Yay! We're in, well, whichever function. On AMD64, they call it hammer time because I think it was the first hardware was the hammer. Or there's something early on that was called the hammer. We just called it in ARM on ARM. I couldn't come up with a fun name. Yeah, so we're definitely more than just local.s. You need to do a few things though in C. You can't just start running code, your machine independent code. You pass data, there's some data gets passed from the loader to user space, to the kernel. Things like your DTP, or ACPI tables now, but at the time it was just that. You need to pass in physical memory locations. So we need to know whereabouts to actually assume memory is, because we don't know, we don't happen to know. We ask EFI and loader.efi, and then that will tell us. So you need to do that. You need to do some bootstrapping. You can do some of that in assembly. It's a lot nicer if you can do it in C though. You need to turn on the console. It's nice to have printf running, working. There's a few things like proc0, which is the kernel process in the initial thread. And there's a few functions, random tuning functions. You just call and you just pretend you know what they do. You don't actually, it doesn't particularly matter. It's just called early on. And luckily, once you've done this, you can enter machine independent code. And you find pretty quickly you need to actually do more virtual memory. This is just a story of virtual memory, I think. There's a layer of machine-dependent code called pmap. This is what translates, that's what creates page tables. So it's asked to say, you have the virtual memory management code that goes and asks pmap to say, create me this mapping, or tell me some information about this mapping, or things like that. I thought, AMD64 looks really complicated. I'll try writing my own to see if it can do it simpler. You do that, and you fold in a few more instructions, and eventually you get to this thing and say, oh, I can get to mount root. I managed to boot the whole kernel. But then you realize there's a reason for complexity. PMAP's really complex, even if you write your own. You just start and then you think, okay, I'll try something. I'll try reusing AMD64s. And userland just magically works. You get into, it's complex for a reason. For a long time, it took me I was saying, why is I had to get my head into this. It took me a day just to get back into PMAP, looking at PMAP code. But eventually you get to userland, and then you've got the problem. What userland? You've got to actually write all of this suddenly. So you've got a few things. So the very first code you get in the static binary is a thing called CSU, so the C support utilities, something like that. It means something, I'm sure. libc is fairly important, and eventually you want the runtime linker, so if you want dynamic binaries. CSU's first code, it could be run, there's a couple ways. It's directly loaded from the kernel, if it's a static binary, or via RTO, the runtime linker, if it's dynamic. It does loads argv argc. It's not just magically put into by the kernel. They're stored on the stack, and then you have to find them. And there's a few things like init and fini, which are old ways of doing pre-main and post-exit or on-exit handling that we needed. It tends not to be used nowadays. But you still need them just in case you've got some old tool chain that uses it. And you need to do both sides of syscalls. So luckily, FreeBSD just generates them from syscall.master, but you still need to tell it how do you do a system call. And long jump, set jump. There's a few misc functions here as well. And then you get into init. So maybe this is the start. We've actually now running C code, user space. And luckily, around this time, I got made redundant, which is great because FreeBSD Foundation said, we've got some money. Do you want to have it? Well, not all of it, obviously. They wanted some. And Semi-Half as well, who's a consulting company in Poland. Poland. So we did this project to actually make FreeBSD arm64 a real thing, not just. I think at the time I was building partway through. I think the instruction would say start building, use this build world, but you probably won't get the whole way through. Doesn't matter. You only want a few bits of it anyway, and so we wanted to actually be able to build everything. So we did. There were 3 parts. There were 3 parts we did mostly simultaneously. We did some more kernel bringup, so other part. We didn't just. I just got the minimum to work. We wanted to actually get something usable by more hardware. We did more user space bringup, so we could actually run the whole user space. And there was also, we used the ThunderX as a reference platform because some of it was funded by Cavium, who built ThunderX. So this was about 2014. So this was almost 10 years ago. So maybe this is, if I'm saying 10 years of FreeBSD arm64, this would be the right date. And this was also the first time someone paid me to work on FreeBSD. So everything up to this point was just evenings and weekends. So this was all done in the FreeBSD Foundation GitHub. So there's a branch in there. There's a few branches in there. One's, I think it's an ARM64 branch, if you want to have a look at old code and how the process we were going through. I was mostly faulting in these functions that I just implemented as panic, and as I kept finding new functions to implement, I'd handle them. Both the user space and the kernel. So working on getting more of the kernel implemented and more of user space implemented. And we had an ARM64 to do comments, and I think we may still have a few of them around. There might be in some weird obscure corner cases that I think I saw an ARM to do panic actually when I was doing a grep for them recently in some obscure corner case which we must not hit. So Semi-Half, I think they focused more on ThunderX. So it was useful for that, in that it was actual hardware, and it implements things that the model may not. I was working on the ARM model at the time. So we did, floating point, gigv3, DDB. That was gigv3 and DDB. I think it was Semi-Half. We renamed to AR64 because software expected that, and we were building with Clang. I think we still definitely needed external bin tools. And then that project went well. So maybe is this the start of ARM64? This was importing the kernel. It wasn't the first ARM64 change in the tree. But this was bring in the kernel. Okay, we can now. There were a few more changes after that, obviously, and user space had to come in as well. But should we consider this? Could we consider this the start? But as I said, we did make some decisions. We have to make some decisions when doing this. We need to boot with. Need to boot with UEFI initially, just because it's so much easier to have someone else deal with the early boot things. And we don't need to worry too much about dealing with having to figure out what mode are we in when we enter the kernel. We did CPU start with a tool called a thing called PSCI, which is a way of calling into EL3 to ask it to do things, to do power management for us. So they would do CPU on. There was another method called spin tables where all the CPUs are running and everything that's not the boot CPU is just spinning on waiting for you to write to a specific piece of memory to tell it where to jump to in physical memory. The issue is that it doesn't give you any feedback as did it actually work. So I ignored that to begin with. That's now, those two are both being changed now. We can build a boot I image pretend to be Linux and boot from U-boot, and you can use spin tables. We only targeted FTT, so you assumed you had a DTB. We fixed that fairly early on to also support ACPI because FTTs are common in the consumer devices, in your mobile phone type devices, but ACPI is preferred in servers. So those top three have all been, there was some early decisions we made, but they've been changed since then. And as I said, I implemented functions as needed. That makes things so much easier not to have to do everything all at once. Hit them as you hit things, figure out how do you actually implement this? How do you test this? Because if I just go and write everything, I don't know, am I actually hitting this? Is this going to work if I do hit it? Yeah, as I said, I did a wee bit more project for the foundation. We wanted to expand virtual address space to 48 bits. ThunderX everything on ThunderX was cache coherent. So DMA was all cache coherent, all the devices. We didn't have to worry about forcing everything out to RAM because the device you're talking to doesn't talk to the cache. Since when we started this, I wrote a simple IRQ handling framework. Since then, IntraNG moved into the tree and became sort of machine independent. It was ARM and MIPS, I think, were the first two. So we did we updated the drivers to work with, and ARM64 to work with that. We did some super pages. So these are, if you've got a 4K base page, you can put together, and you've got them all, and you allocate your physical address space in the right way. You can put those together into a 2 meg super page, and it reduces TLB usage and ACPI. So we need a few things for IntraNG. We'd brought in GigV. GigV2 driver was already supported, and we just needed to do the GigV3. We needed to support MSI and MSIX interrupts because we've got PCI, and so we needed to pass the range. And the way the GigV3 works is there's a separate thing that normally handles. There's another thing called the ITS, which just handles MSI and MSIX interrupts. And eventually we could just remove my old code. It was probably a best idea. And I said super pages, we did that. The issue you've got with super pages and ARM64 is we have a thing called a break before make sequence. So you have to remove the old entry, do a TLB invalidate, create the new entry. What happens if another CPU accesses that entry, that virtual address at the wrong time? Hopefully you can do this quickly enough. That's very rare, but it's going to happen, so we've got to handle that. What we do is we just enter the kernel, enter the exception handler, check, does this entry actually exist now? And if so, just return, because we're probably in that sequence. And there's lots of issues with this in the kernel, which we have fixed, luckily. So we disable it in the kernel. It's just because until you find them all, it's very difficult. So, first release, was that the start of FreeBSD? I think this is probably getting a little bit too late at this point. We're saying, yeah, releases a wee bit a bit late for saying the start of something. That's the start of something other people can use in an easily usable format, maybe. So our first release was FreeBSD 11. It was prior to this, we'd originally put in sbreak and break calls and decided they'd been removed from POSIX years before, before ARM64 was a thing. Do we really need these? Emacs seem to not like that, because there's an email here at 30 saying that when told that these had been removed, they said, "Are they mad?" So I think that's as a Vim user of Vim, I think that's a badge of honor. I considered, yeah.
Could you implement it based on mmap in user space?
They did something. So the question is, could we do an mmap in user space? They were using sbreak, I think, was to find the end of code. So my understanding is that the way Emacs was worked is when you built it, they intentionally crashed it to create a core file, and then used sbreak to load it, to get some address to load the core file back in. To basically, rather than having to do some expensive startup, they could just load the data once. So we could implement those with mmap, sbreak and break with mmap. It would still break Emacs, though, I think, because of how they're using it. So we have discussed in the past, and I think Brooks has suggested we do maybe have a library for this that does, if people want it, implements it, sbreak and break using mmap. Or maybe we just have one that returns the failure every time. Or in our case, just not have it. So I consider FreeBSD 11 was a nice technology preview, but it was not the best. This was only we hadn't spent much time on any polish on this. It was more of throw the code into the repo, see what happens. So yeah, Float 12 was a couple of years later. We could support, if you want to do anything like, say, kernel crypto, is someone like, say, Netflix uses this sort of thing in some of their models where they want to encrypt data before sending it out on the network. So you may want to be able to do kernel crypto for this. But the ARM64 instructions assume you've got floating point enabled. They want to be able to operate on floating point instructions. So we needed to get AES support, we needed floating point in the kernel. There was, luckily, AMD64 support, and it's just translate that to make that, I think it might have been PowerPC as well, just make that look ARM64-like, and sort of mostly just works. This was when we had ACPI come in. So you could build it, you could run on your servers. We did PAN, which is by default, the kernel has enough privilege to be able to read all memory in the system. What PAN does is says, if user space has write access to this address, we want to disable, when we have PAN enabled, we disable privileged access, so the kernel can't access that memory. That is great, except one case of execute-only memory, which we don't have. So it stops you, it catches a lot of bugs of doing mem copy rather than copy in. If you're writing kernel code and you just mem copy user space memory, that will fail if you've got PAN, which essentially all modern hardware will have. We execute never, so make sure your data is non-executable. We did some early NUMA, there's some EFI runtime services, and I think there was like the early Linux emulator was in there as well. So running Linux binaries. on FreeBSD, user space binaries. And then we'd done enough work. We got tier 1 and managed and demoted i386 to tier 2. So we still only have 2 tier 1 platforms. We wrote I think it was Olivier or someone wrote Combat 32, so you can run ARMv7 binaries on ARM64. You definitely can't run ARMv4 and 5. You might be able to get ARMv6 if you're lucky. I haven't tried it.
It does work, but the kernel only advertises ARMv7.
So the answer is that ARMv6 does work, but the kernel only advertises ARMv7, which, given I've just removed ARMv6, is probably I have no problem with. We did some there's some ACPI updates. There's some Gig v3 driver updates. There's always PMAP update improvements. We managed to get finally got super pages working in the kernel. There's some issues around making sure that your exception entry point doesn't hit you don't promote the memory that the exception entry point needs to access to be able to handle the exception. Because of the same issue is you'll get an exception, and then in your exception handler, you'll get an exception. And in your exception handler, you'll get an exception. Johnson did LSC atomics. So these are atomics on ARM64 is pure ARMv 8.0 is load exclusive, do some operation, store exclusive. If that memory has been touched, the store exclusive will fail. LSC atomics say do certain operations atomically in a single instruction. So it can have a load and store in a single instruction. And we did some boot-I. We got boot-I support. So this was booting. We can build the kernel as a Linux image and boot it from that. I did a per thread stack canary. So FreeBSD kernel has stack canaries, but on ARM64, there's a single stack canary for the entire kernel. So you could potentially have cross-threaded attacks that way. ARM64, we have a single stack canary. Each thread has its own canary, so you have to figure out what it is per thread, not globally. I did pointer authentication, so when you enter a function, it can sign the stack pointer and signs based on stack pointer and link register the return address. And then on exit, it will authenticate that and either raise an exception or.
Do we have any user space software that actually uses that?
User space software, I'm not sure if we enable it. We do enable it in user space now. Yeah, everything in the base system has it enabled. Another question?
Does the 16K page size effectively provide a new ABI?
So does the 16K page size effectively provide a new ABI? Yes, if you're assuming page size, the macro is a static thing. There is a function to ask the page size you're running. We've mostly got rid of the page size use from the kernel, from user space, except JE-malloc is the pain because it needs to hard code it for JE-malloc reasons. And I am slowly working on trying to remove page size macro from visibility from user space. But there's a few other things around pipes and a few other libraries that need it. I think this is when we got some initial Azure support, and we actually now allow spin tables. And initial ECMI patches, which is a way of talking to some management hardware. And if you're interested in that, there's a talk tomorrow on further work on ECMI. More improvements. And also, there should be 15, sorry. This is So we have ECMI improvements, which will the talk be on. Random number provider, BTI, which is when you jump into a function, it has to be on a specific instruction. You can't just jump into the middle of a function. We find that we've got beehive support. So if you, most of your ARM hardware, except for Ampere emag, should just work. Ampere emag is known to be buggy, or FreeBSD on Ampere emag is known to be buggy. There is both using ARM v8.0, which you go to the hypervisor and back out, and VHE, where you run the kernel in the hypervisor level, so it should be quicker. We did watch points. We added watch point, and we're adding hardware trace. That's something Ruslan's working on, and we've got Zachary Lee from ARM has done SPE support, the statistical profiling. So it will statistically sample instructions to find and give you information about execution time. So it can be useful for finding where you've got a loop of code that's running regularly that's slow. And Ruslan added the core site with the hardware trace. And almost have SVE, which is take neon or the floating point and just make the registers much bigger. And basically a multiple of 128 bits. But it's hardware sized, and we do get some choice on software and to reduce the size if we want. But it's big. It tends to be bigger bigger registers. So in theory, it should be. It helps in some cases, some situations. But I couldn't tell you what because I'm a kernel engineer and I don't do floating point, except in very specific cases. I expect to start MTE soon. So if you, but also looking in future direction on what people. So MTE is tagging pointers for deterministic. It's kind of ASAN-like thing in hardware. But we're also looking at future directions of what people are interested in the current architecture. So when did it start? I don't know. Sometime 10-ish years ago. One of these dates, maybe, none of them, somewhere in between. I will leave it up to anyone to decide. And I'd like to thank a few people. The FreeBSD Foundation, they organised a lot of the early work of doing this and getting things working. And the University of Cambridge Computer Lab for running basically the Morello project. So telling Robert Watson there, employing me to make this more production ready. Just work on this, get things ready for Morello when it starts. And if you haven't worked out, they now employ me. I'm now a software engineer there, working on the kernel. But they also have they funded some of the work through the foundation. And so, yeah, thank you. Are there any questions other than, yeah?
How far out do you think you are for ARMv9 and SVE2 support?
ARMv9, SVE2, well, ARMv9 should just work because it's compatible with ARMv8. SVE2, I had a look. I don't think there's any new, everything's just new instructions as far as I can tell. So unless I'm missing something, then it should just work once we get SVE, because it's just some hardware caps to tell the user space that's there. Yeah?
Is anyone working on GIC-v2 support in Beehive?
GA?
Interrupt controller.
The what, sorry? The
Something like a Raspberry Pi with Beehive and other SPCs, which still use it.
the GIC-v2. I added support for it means that we don't just have GIC-v3, but I have not done GIC-v2 support. I looked at that and I thought if someone really wants to, they can do it. I prefer not to touch it. But I don't know of anyone that has plans to do GIC-v2. Yeah?
What's the current timeline for the continuation of AH32 support?
A contentious topic. I couldn't, so there's questions on timeline of AH32. I couldn't comment on any future decisions. Mostly I don't know. Questions on IOMMU, anything about it? We were looking at cleaning up some things. It mostly works except we need to handle MSI interrupts from it because Ampere Ultra has an MSI rather than a normal interrupt. So I think that's probably the only thing that's missing from that. So if you want to implement that, I'll be happy. It means I don't have to. Yeah. So power. Power saving. Yeah. Anything about it?
That stuff that's in the ACPI table.
So there's some ACPI power saving things which I don't remember exactly what the acronym was off the top of my head. I can add it to my list of things to look at. I don't think we have it. We haven't had time to look at it just yet. I have got last question on my screen here.
It's a list of known working boards.
Is there a list of known working boards? The FreeBSD wiki has a list of boards. Whether they're working or not in the current version, Raspberry Pi 4. Yep, thank you. I think we've run out of time, unfortunately. If you've got any more questions, I will be around.